So the second half of 10.3 is on this idea of the empirical formula. So the empirical formula is defined as the lowest whole number ratio of elements in a compound. And for all those ionic compounds that we talked about in chapter 7, the empirical formula is really what we were talking about, right? When we say NaCl, we know that every individual crystal of salt has a different number of Na and a different number of Cl in it, but the ratio is always 1-to-1. And so this is true for every ionic compound. But for molecular compounds, remember the formula is a little bit different. It's the actual number. And several compounds can actually have the same empirical formula. If you look at these three on the right, ethanoic acid, methanol, otherwise known as formaldehyde, and glucose all have twice as much hydrogen as carbon, right? So they all have what we would call the empirical formula of CH2O, right? Don't they all have the same smallest whole number ratio of elements in a compound? So what does this mean? Well, the empirical formula is not really something important that you need to know. But we use it in order to find the actual formula of a compound. So this is when we answer that question, how do we know that water is 2 hydrogen and 1 oxygen? How do we know that salt is 1 Na and 1 Cl? This is how we know. What we would do is put the sample into an instrument, and the instrument would do all sorts of things. Sometimes we'll separate them gravimetrically, meaning like by mass. You could put charges on the atoms and do all sorts of things. But at the end, what comes out the other end is a percent composition. And so we would get that percent composition and then do some calculations and eventually come out to an empirical formula. So this is going to be finding the empirical formula from percent composition. And it's three steps. So you want to put these 3 steps in your head. Assume a 100-gram sample. What does that even mean? It just means change the percent sign to gram sign, basically. Convert to moles, divide by the lowest number of moles. That will get you the ratio of the elements in the compound. What is the empirical formula of a compound that is 40.5% sulfur and 59.95% oxygen? So remember the 3 steps. Assume a 100-gram sample, convert to moles, and divide by the lowest number of moles. Those are those 3 steps that we're going to go through. When we say assume a 100-gram sample, if I had 100 grams of this compound and I know 40.05% of it was sulfur, well, that would mean that 40.05 grams of it must be due to the sulfur, and the other 59.95 grams of it must be due to the oxygen. So that's the first step. Convert to moles. Okay, we know how to do that really well now. 1 mole, and the molar mass from the periodic table on the bottom. And this you want to write out, in terms of where do I round? Well, right now you don't round at all, because we're not at the end of the problem. And we know that we don't round until we get to the end of the problem. So you want to use as many digits as you can, and especially in your calculator. So now we've just converted grams to moles, and now we do that last step, divide by the lowest number of moles. So which number is smaller, 1.24 or 3.74? And of course that's 1.24. So I will divide both by 1.24. And I'll try to use as many digits as possible so I can get as close to whole numbers as possible. So this comes out to 1, and this comes out to 3. So what does this mean? So this is 1 sulfur and 3 oxygen. That means in this compound, there's 1 sulfur and 3 oxygen, SO3. What order do they go in? Usually I'll give them to you in the order I want them back. The rule is the least electronegative element first. So that's how we do these, the least electronegative element. So right, assume a 100-gram sample, which just means put a gram sign. Convert to moles, we know how to do that. Divide by the lowest number of moles. That will give me the ratio. Here's another one. What is the empirical formula of a compound that is 81.79% carbon, 6.10% hydrogen, and 12.11% oxygen? So if you feel confident, maybe give this one a try on your own. If not, follow along with me. 81.79 grams of carbon, 6.10 grams hydrogen, and 12.11 grams of oxygen. So take a look what I did. Assumed a 100-gram sample, converted all of those to moles, and then divided by the lowest number of moles. Now, if you don't get exactly whole numbers, they should be extremely close to whole numbers. And remember, we're talking about number of atoms, so they can't be anything but whole numbers. So 8.99, that's going to round up to 9. Same thing with 7.99. So our formula is C9H8O. Now, those came out to be really nice whole numbers. Unfortunately, it doesn't always work out that way. And this is an example of that type of problem. So we're going to do the same thing, but we're going to notice at the end that it doesn't work out to all nice whole numbers. So you can see the problem here is that I got 1.499 moles of carbon. And you may think, well, that should just round, right? 1.499, well, 1.4, you know, like how does that round, up or down? Think about that number and how far away it is from the number 1, which is one thing that you could round it to, or how far it is away from the number 2. And it's actually very far away from those numbers, pretty much as far away from those two numbers as you could be, being in between them. So we don't round. That's really far to round. Think of this as 1.5. Now, if you think of this instead of 1.49, you think about this as 1.5 or 1.5. Another way to think of that might even be 3/2. Can I multiply? Like, I want to keep these in this ratio, but I want to get whole numbers because these need to stand for atoms. There's no such thing as 1.5 atoms of carbon, just like there is 1.5 moles of carbon, but there's not 1.5 atoms of carbon. So what am I going to do here? Well, if I want to keep the same ratio, but I want to get rid of the decimal, right? If I multiply 1.5 times 2, that equals 3. If I multiply all the other ones by 2 as well, I will keep the same ratio, right? So instead of 1.5 carbon, I would have 3 atoms of carbon. 3 times 2 is 6 atoms of hydrogen, and 1 times 2 is 2 atoms of oxygen. So C3H6O2. Right, smallest whole number ratio, but it actually is not the, but you have to do that little trick. So that anytime one of your, when you divide by the lowest number of moles, if it comes out to be 1.5, or it comes out to be, let's see, if it comes out to be 1.5, you multiply it by 2. If it comes out to be 1.333, right? That's really 1 1/3. You would multiply that by 3. Or 1.666, you would multiply everything by 3 as well. Those are the only ones that really ever come up. And so this actually doesn't give us the final answer because as we saw on that first slide in this video, there can be multiple compounds with the same empirical formula. So how do I know what the actual formula, the molecular formula is? Not just the ratio, right? How would I distinguish between, these were the 3 on that front slide, right? How do I distinguish between those? And the way we would distinguish between those is by their actual molecular mass. What I would do is I would find the mass of those. And I would notice that the mass is going to be much larger than the mass of the empirical formula. And how much larger? Well, what I'm going to do is I'm going to divide the mass of the molecular by the mass of the empirical, and I should get some whole number. That tells me, well, the real formula is 3 times as big, is twice as big, is 6 times as big, a number as big that you were going to then multiply all of the subscripts by. So to find the molecular formula, you need to find out how much bigger that formula is in the empirical. Like I said, twice as big, 3 times as big. And so you take the experimentally determined molar mass of the compound. This is going to be given to you in the problem. And you divide that by the mass of the empirical formula, which you're going to need to find using the periodic table. And then that number will be 2, 3, 4, 5, and then you would multiply all the subscripts by that. So this is the chemical formula of nicotine. It contains 74% carbon, 8.65 hydrogen, and 17.35 nitrogen. Here is the molar mass of the actual formula. So this is going to be on the top. I need to divide it by the molar mass of the empirical, and that will give me the ratio that I multiply everything by, right? So if I think of using this formula right here, right? So the mass of the compound over the mass of the empirical is how I'm going to end this problem. So I'm going to take 162.26 and I'm going to divide it by the mass of the empirical formula. Problem is right now I don't have the empirical formula, right? So I'm going to do the exact same 3 steps that we did before. Assume a 100-gram sample, convert to moles, divide by the lowest number of moles in order to get the empirical formula. Right, so I went through those 3 steps, assumed a 100-gram sample, converted to moles, divide by the lowest number of moles, and I get the empirical formula, C5H7N. And now that is not, or that may not be, I don't know yet, the actual formula of nicotine. So what do? I take the mass of the compound, right, that will always be given to me in the problem, and I divide it by the mass of the empirical. So in my calculator, to find the mass of the empirical, I take 5 carbon, 5 times 12.01, plus 7 times 1.008, plus 14.01, and I get the mass of that empirical formula, 81.116 grams, right? That's the mass of that guy. When I divide these, I will get a whole number. In this case, I got the whole number 2. That tells me that it's not C5. The actual formula is C10. H, not 7, but 7 times 2, or 14, and not N1, but N2. This is the actual formula for nicotine. 10 carbon, 14 nitrogen, and, 10 carbon, 14 hydrogen, and 2 nitrogen. Okay, so find the empirical formula. Sometimes I think on the homework, the first one, I give you the empirical formula. But you find the mass of that, right? And that's on the bottom. The mass of the actual formula on top. Divide, you will get a whole number. And then you multiply all the subscripts by that. This last problem here is for succinic acid. We get its percent composition. Carbon, hydrogen, and oxygen. We get its molar mass, and we want to determine the empirical formula and the molecular formula. So I know at the end, I need to take the mass of the compound, the molar mass of the compound, over the mass of the empirical formula. So we already have one piece of that, 118.1. Now I have to find the empirical formula in order to find the mass of the empirical formula. So I'm going to do those same steps that I have done before. So after I did those 3 steps, and this was one where we actually, when we divided by the lowest number of moles, one of my answers was not a whole number. It was very close to 1.5. So then I recognized, okay, this is one of those where I need to multiply everything by 2, and I get the empirical formula to be C2H3O2. And then the question is now asking me, what is the molecular formula? So I find the mass of this, right? The mass of this, 2 carbon, 3 hydrogen, and 2 oxygen, turns out to be 59.044. And so when I divide those, it equals 2. It doesn't always equal 2. I know that it was the last example and this example, but it's not always 2. So that means I multiply each of the subscripts by 2. So the real formula for succinic acid is C4H6O4. That's the true formula of succinic acid.